Hey everybody, I'm excited to talk to you about the finite difference method for solving seepage problems. In this first series of videos, we're going to explore the basic formulation of the finite difference equations and look at boundary conditions, and then in part 2 we're going to look at more complex cases and also look at solution techniques. So, thus far, we've been looking at flow nets and analytical solutions as solutions to the governing equation for seepage problems. And those you can do a flow net for relatively complex cases, but it's a little challenging to set up. Analytical solutions only work for really simple geometry and material properties. But for more general problems, we employ a numerical technique. And there are two numerical techniques that are generally used to solve our governing equation, which is this is a steady-state version of our 2D seepage equation. One of which is the finite difference method, and which we'll explore in this next series of videos. And the other is the finite element method, which we will also explore this semester. So the way the finite difference method works is you discretize your problem into a series of cells. Typically, they are ordered in rows and columns. And there are two ways to formulate the cells. This is a cell-centered finite difference grid. Now, by the way, this is the classic partially penetrating sheet pile problem, which the solution is symmetric around that vertical line coinciding with the sheet pile. So you can solve the whole problem domain if you want, or you can solve for half of it, and the flow rate you get for this half would be the total flow rate. And if you mirrored the head solution to the other side, you'd have a complete solution. So this is a cell-centered, what we call a cell-centered finite difference grid, and this is what we call a mesh-centered finite difference grid. The difference is what is the focal point of the formulation of the finite difference equations. With a mesh-centered approach, we are solving, we have a separate equation for the head at each of these cell centers relative to the neighboring cells and their centers. And with a mesh-centered grid, we focus on the corner points of the grid. And again, we reference these nodes, which are the corners of the grid cells, up and down and left and right. It turns out for the particular formulation that we're going to be focusing on primarily in these videos and in our exercise and homework, we will mainly be looking at mesh-centered finite difference grid. But again, there are rows and columns. There's always something to the left and right and up and down. And so what we're going to do now is we're going to explore how to formulate the equations. And the way these numerical methods work is we formulate an equation for the head at each of these nodes and relative to the heads at neighboring nodes, and we do it in such a way that satisfies the governing equation. And that gives us a set of equations, one for each of these red nodes, which we then solve. When we're going to talk about different solution techniques, but you essentially have a whole bunch of simple equations, and you modify some of the equations based on boundary conditions, and then you solve the equations. So how do the boundary conditions work? Let's suppose that we have 30 feet of head on the left side and 23 feet of head on the right side. The head at this point right here would be 26.5. Well, how did we come up with that? This again, we're only solving for half of the problem, and since this is symmetric, by the time the water flows down the left side toward the right, once you get to this center point right here, the head would be exactly halfway between the upstream side and the downstream side. So if you take halfway between 30 and 23 is 26.5. So we could put a specified head boundary condition right here of 26.5. Up here we know what the head is, so that would be 23 feet. So we don't need a special equation for these nodes. We just immediately assign the known head value based on the boundary conditions. And then over here on the right, what do you do with that boundary? Well, you could, if this boundary is far, most of the flow is going to occur right around the sheet pile. So once you get out a certain distance, there's very little flow. So you can either take the head up here and assign that as the specified head boundary, or you can treat it as a no-flow boundary, either way. And then all of the other boundaries are no-flow by default. So this is a no-flow boundary up the side of the sheet pile. This is a no-flow boundary down here on the bottom. And so now we're all set with our boundaries. Okay, so next, now that we've set up the basics, let's talk about how we formulate the governing equations. And there are actually two methods for formulating these equations, and we're going to explore both of those. The first method relies on approximating first and second derivatives. So now we're looking at one of these nodes. So if you go back to this equation, if you just take one of these interior nodes and look at the nodes above and below and to the left and the right, that's what we see here. And to start with, we're going to assume that we have a spacing of delta x in the horizontal direction, a spacing of delta y in the vertical direction. And notice how these nodes are labeled. This is node I here in the center. We're going to be deriving an equation for the head at node I. And this is L for left, R for right, A for above, and B for below. So our objective here is to formulate an equation for head at this node that satisfies this governing equation. And you'll notice that I've gotten rid of the k terms, the kx and the ky. So we're assuming, for the sake of this derivation, that we have isotropic conditions. In part 2, I'm going to show you how to go back to where kx does not equal to ky, but we're going to start, this, assuming it's isotropic, makes our derivation a lot simpler, so that's what we're going to begin with. And so the first thing we do is we approximate a set of first derivatives. And so we're going to assume that water is flowing from L to I and then from I to R, and from B to I and from I to A, so left to right and from bottom to top. And so if you can approximate a derivative, the first derivative going from L to I is HI minus HL over delta x. So this HI minus HL, if you take the head where you end, subtract the head where you begin, that's the change in head. So HI minus HL over delta x, that's the essentially the hydraulic gradient, the first derivative between L and I. Likewise, to go from I to R, we take HR minus HI divided by delta x. And then down here, going vertically, we do HI minus HB divided by delta y. And then HA minus HI divided by delta y. So again, just a very simple representation of effectively the hydraulic gradient, or the first derivative of head in the x and the y direction for each of these four relationships between the nodes. Now, the next thing we need to do is approximate second derivatives. Okay, the second derivative is the derivative of the first derivative. So it's the rate of change, it's how the first derivative changes. Right? So when we approximated the derivative from L to I, we effectively approximated it right here, the halfway point between the two. And when we approximated the first derivative from I to R, we effectively approximated it this black dot on the right. And those two are separated by a distance of delta x. So if we want to get approximate the second derivative as you go in the horizontal direction, if you take this derivative on the right, hr minus hi over delta x right here, and subtract the derivative on the left, and then divide that by delta x, you've approximated the second derivative. Again, the second derivative in a particular direction is how the first derivative changes. So the ending first derivative minus the starting first derivative divided by delta x. So that's represented over here. And then we plug in these first derivatives that we found in the previous step. And then if we simplify that, we have hr plus hl minus 2hi over delta x squared. That is this approximation of the second derivative in the x direction. And likewise, in the y direction, we have ha plus hb minus 2hi over delta y squared. These are the two components of our governing equation, so if we just throw those into our governing equation, second derivative for x, second derivative for y, and then, again, our objective here is to get an equation for h sub I. So now we have an equation for hi that is a function of hl, hr, ha, and hb. So it factors in the delta x and the delta y. And a really cool thing is if delta x is equal to delta y, you can replace all of these deltas by delta x's and delta y's by deltas and simplify. You end up with this beautifully simple expression. The head at the node is 1/4 of the sum of the heads at the surrounding nodes. In other words, it's just a simple average of the heads at the surrounding nodes. So again, this is with delta x not equal to delta y, and this is for the uniform spacing. And again, we've got an equation for the head in a node relative to the heads at the adjacent or neighboring nodes. And we repeat this for all of our grid nodes, and we have our full set of finite difference equations that we can then solve.